All right, so we've made it all the way to topic 15, which is about rewriting radical expressions using their properties. Now this is the property list I gave you in your 6.4 notes. If you don't have your 6.4 notes in your notebooks, please look at the 6.4 notes on Canvas so you can remember what these radical properties are. Our first problem is going to be to circle an expression that's equivalent to 16 to the 1/4 power times 16 to the 2/3 power. Now when I have like bases, all I have to do is add their exponents. Just like if I was doing x squared times x cubed, that's 2x's times another 3x's, we get x to the 5th. We just add these exponents together. This time, our exponents are fractions. So this is going to be 16 to the 1/4 plus 2/3 power. And the only gross thing about this guy is trying to add those two fractions. But all we have to do to add fractions is to get a common denominator. So 1/4 plus 2/3. These denominators don't have anything in common, which means what they're missing is each other. Oh. So 4 needs a 3, so we multiply by 3 over 3. This 3 needs a 4, so we multiply by 4 over 4. That turns this into 3 times 1, which is 3 over 12. And over here, 4 times 2 is 8 over 12, which gives us an 11 over 12 as a new exponent. So this is 16 to the 11 over 12. Now all of the possible answers are written as radicals, so we have to remember what the fraction radical means. The numerator is what we raise 16 to as an exponent, and the denominator is what we root 16 to as an index. So 16 to the 11th power and the 12th root, which is a. All right, up next, we're going to try and perform this operation. So we're trying to do subtraction with these radicals. Remember, if I'm multiplying radicals, they just need the same index. But if I'm trying to add or subtract, they need the same index and the same radicand. So they need the same number inside and the same index on the outside. And none of these so far appear to have that. So I need to simplify these first before I can figure out how to combine them. So we're going to do that starting with 3 times the root of 45. I'm going to break 45 down into pieces. 45 is 9 times 5. Now I can either keep breaking until I find pairs of things. Remember, no index means it's an index of 2. So I can break 9 down to see it's 3 and 3, or I can just recognize that 9 is a perfect square and I can bring it out of the radical as the number 3. So 3 has to come out of this radical. I already had a 3 in front, so those get multiplied together. I end up with 9 out front. And this 5 is stuck inside the radical. So 9 root 5 minus 2 root 11 minus 3 root 5. Now, we can only add and subtract radicals with the same index and radicand, and the only radicals that have that are the square root of 5 here and the square root of 5 here. So this says we have 9 things called the square root of 5. This says we should subtract 3 things called the square root of 5. So altogether we end up with 6 things called the square root of 5. And the 2 root 11 doesn't have anything it matches with, so it's done. It can't combine with anything, and we're finished. Now, the only reason I didn't break down 11 or 5 is because they are prime numbers. 11 times 1 and 5 times 1, and we can't break the numbers down any differently, so we're not going to have any pairs or triples or anything. So once you have prime numbers, you don't have to break them down at all. All right. Let's take a look at number 51. Perform the following operations and combine like terms. Find the simplified form. Let's see the easiest way to get started here. I think the easiest way to get started is to go ahead and rewrite these as radicals first, just like the previous one is written as radicals, and then simplify and see if we can do anything. So I'm going to go ahead and rewrite this. 8 to the 1/2. Remember, the numerator is an exponent, so 8 to the 1st power, which is just 8. And 2 is the index, that's the root, so that's the square root of 8. For 16, 1 is the exponent, that's 16 to the 1st power, and 4 is the root, so that's the 4th root of 16. Goodness, that was not written pretty. Let me try that again. That is the 4th root of 16. That's a little better. Okay, and up next, 81 to the 1/4. Again, that's 81 to the 1st power and the 4th root. So let's simplify these a little and see if we can do any addition here. All right, so let's go ahead and see if we can simplify these guys. 8 is 4 times 2, and 4 is 2 times 2. Because this is a second root, we're looking for pairs. So 2 can come out of this radical, and this guy too is left inside. So 2 times the square root of 2. Up next, let's take a look at doing that for 16. 16 is 4 times 4, and 4s are both 2 times 2. Goodness, these are 2s. Sorry about that. And this is also 2 times 2. Now this is a 4th root, so I need 4 of something, and I have 4 2s. So that's actually just the number 2. Easy peasy. Same thing is going to actually happen over here. The 4th root of 81. 81 is 9 times 9, which is 3 times 3. And 3 times 3, I have 4 3s. So that's actually just going to be the number 3, and I don't have anything stuck in my radical. Now remember, to add and subtract radicals, we have to have the same index and radicand, and the only things I have with the same index and radicand are these guys, because they have no index and no radicand. So I can combine these two numbers to get 5, and then 2 root 2 is the only one left. So that one can't combine with anything. So that guy's all done. We have one problem left for radicals. Let's go ahead and have a peek here. We have to do some simplifying. So it says to rewrite in radical form first and then to simplify. So let's go ahead and take a look at that. We have 24 times x to the 5th to the 1/3 power. Now this exponent on the outside, the numerator, is what we raise it to. So 24x to the 5th gets raised to the 1st power, which is just going to stay the same. And the denominator is what we root it to. So this is the 3rd root. So we're going to start breaking this guy down. To do the number 24, I'm going to break it down in pieces like we're used to. 24 is 8 times 3, 8 is 4 times 2, and 4 is 2 times 2. So what we see here, we're looking for 3 of the same thing. I have 3 2's right here, which tells me a 2 will be able to come out of this radical. But this 3 will be left inside. Now before I finish doing that up, I'm going to go ahead and take a look at the x. And remember, when I have variables, I can do them differently. I can either write out all of the x's and circle my groups of 3 to see how many I can bring out, or I can use the long division process, which is much faster. I just look at the exponent of my x, that's how many x's I have inside, and I divide it by the index, which is how many I need to bring something out. What I get up top on my division is how many will make it to the outside. So 3 goes into 5 once, which tells me 1 x can come outside. Whatever my remainder is tells me how many x's are stuck inside the radical. So 3 times 1 is only 3. I have a remainder of 2, which tells me that there's x squared stuck inside my radical. So let's go ahead and take a look at the radical here. 2 has come out, x has come out. I still have a 3rd root happening. I had an x squared stuck inside, and because of this guy, I also had a 3 stuck inside. So 2x times the cube root of 3x squared. So that one's all done. Let's go ahead and try it out for question B. Again, I have the 1/4 power, so that's the first power. So 80 x to the 6th, y to the 12th to the first power won't change. And the 4 tells me the root, so that's the index of my radical there. I'm going to break my 80 up into pieces using factoring. So that's 8 times 10. 8 is 4 times 2. 10 is 5 times 2. And 4 is 2 times 2. In order to bring anything out of this radical, I have to have 4 of them. So I have 1, 2, 3, 4 2's altogether. And this 5 is going to be stuck inside. So I already know that a 2 can come out, and a 5 is stuck inside. Now let's take a look at my x's. Again, I'm going to use division. I have 6 x's inside. I need 4 to bring something out of my radical. 4 goes into 6 once. That tells me 1 x can come out. 1 times 4 is only 4. I have a remainder of 2. That tells me that 2 x's are stuck inside, x squared. Let's do that same thing for y. I have 12 y's. 12 y's inside. I need 4 to bring something out. 4 goes into 12 3 times. That tells me that 3 y's can come out. And I'm going to have a remainder of 0, so there are no y's stuck inside. So that's actually finished, and I just have to put my radical back in. This is the 4th root. So 2xy cubed times the 4th root of 5x squared. That guy's all done. We have one more to work on over here, 4a squared to the 3/2 power. Now I'm going to show you 2 different ways to solve this one. One of them is actually a lot easier. I'm going to show you the easy way first, and then I'll show you the way that's a little bit longer, which will still get you the same answer. So up top here, we're going to do the easy way. What we've been doing so far is raising the numerator first for an exponent, and then using the denominator as a root, which is technically totally fine, but I can also do the root first. It doesn't matter which one happens first, as long as they both happen. So I'm actually going to do my root first. The 2 here tells me that I have a second root of 4a squared. And the 3 tells me that this is all going to be to the 3rd power. Again, it doesn't matter which one happens first. So this way, I'm going to do the root first. The other way we're going to do it, I am going to do the root afterwards. So I'm going to do the 4a squared to the 3rd power, then I'm going to do the root. See, I still have the 3rd power, I still have the second root, but the way I'm going to do it that's actually faster is by performing the root first. And it's because I have to do a square root, and what I notice is both of the numbers are perfect squares. So it's actually really easy to do a square root here. If you recognize that, that's awesome. Otherwise, this other version down here will still give you the same answer. So let's do a square root first. 4 is 2 times 2, which tells me that 2 can come out. A squared has 2 a's. We have to do a second root, so 1a can come out, and there's nothing left inside. So this is actually just 2a. And then all I have to do is the 3rd power. So that's 2 to the 3rd power, which is 8, and a to the 3rd power, which is a cubed. So that's a little bit faster because I recognize that I had perfect squares. If we don't see that we have perfect squares, we absolutely can do it the other way around. So let's go ahead and take a look at that. If I didn't notice that I could do the square root first, I could do 4 to the 3rd power, and then I can do a squared to the 3rd power. Now, I'm not actually going to multiply out 4 to the 3rd power, because when I have to simplify radicals, I have to break things down into pieces again when they come to numbers. So this is 4 to the 3rd power, which is 4 times 4 times 4. And then a squared to the 3rd power, I am actually going to multiply out. So when I have a squared to the 3rd power, I have a squared happening 3 times. I'm going to multiply those exponents. That's a to the 6th. So let's look about breaking this guy up. This is the second root. There's a 2 there. So I have 2 4s. That tells me that a 4 can come out. And then this 4 over here is a perfect square. It breaks down to 2 times 2. So a 2 can also come out. A 6th, I'm going to use my division process. I have 6 a's inside. I need to bring 2 out at a time. So 2 goes into 6 3 times. That tells me that a cubed can come out. And I have a remainder of 0, so there's nothing left inside. So I have nothing left inside my radicals. All of my 4's came out, and my a to the 6th came out completely. So all I have to do is simplify this. 4 times 2 is 8 times a cubed, which is the same answer I got up here. It doesn't matter which way you do it, you get the same answer every time. So that's it for our review of simplifying radicals. We have our very last topic coming up in the next video.